Hello and welcome back to my channel. Okay, so in this video we are going to derive a relation between the load, shear force and the bending moment. So let us first discuss what is the use of deriving such relations. So basically, if you remember my last two videos where I solved two problems based on the drawing of shear force diagrams and the bending moment diagrams, then you will realize that in those problems the loads which were given was quite simple. Like only we had point loads or UDL, right? But what if you have a load something like this? So this is neither an UDL nor a UVL nor a point load. This is something you can call arbitrary distributed load, right? So this kind of relations is essentially used for analyzing these this kind of beams, okay, where the loads are distributed arbitrarily. Okay, so for deriving such equations, let us consider a beam, a simply supported beam, okay, joined. So what is a simply supported beam? A beam in which in one end we have a pin joint and in other end we have a roller joint. Those kind of beams are called simply supported, right? So let us consider an area, or sorry, an element on this beam. I have hatched this portion. So let us consider this element. The length of this element is delta x, which is at a distance x from the origin. I am considering this point, that is my leftmost part, as my origin. Okay, then obviously the other plane of the element will be at a distance of x plus delta x. Okay, so now let us do one thing. Let us zoom into this element. So it will be something like this. Okay, now let's try to analyze this particular element. So the thickness of the element is delta x, and by now you should be knowing that if we are trying to analyze a beam or element, whatever it is, then at the left the shear force will be at the upward direction and the bending moment will at the clockwise sense, right, according to the sign convention. And obviously on the right hand side, like the reaction, the bending moment will be in the anti-clockwise and the shear force in the downward direction. So what else will we get? So the next thing we will get is the loading. So we had an arbitrary distributed load, but if we are considering an element, we will be getting something like UDL, okay, because we are considering a very small portion, right? So let us say this is W per unit. So what will be the total force of the UDL? It will be W multiplied with this whole span. So the thickness of whole span, this whole span is nothing but delta x. So the total load is W delta x, which will act at the center of this element. Fine. Okay, so now let us try to derive the relation between the shear force and the load. Okay, so for that we will take the summation of forces along the vertical direction to be 0. So what are the forces acting vertically? Let's see. So I'll be taking the upward forces as positive and the downward forces as negative. So the very first upward force is V, so plus V. The second, this one is acting in the downward sense, so minus V plus delta V, and this one is also acting downwards, so it will be W delta x. Okay, so negative equals to 0. So V and this minus V will get cancelled, so we'll be only left with delta V, which will be equals to minus W delta x. Okay, so delta V upon delta x will be minus W. So we know as the area, as the value of delta x is very small, so it will be tending to 0. So we can write this. Okay, in the limit form we can write this. So one thing that I forgot to tell you guys, that is I have considered this as V plus delta V and this is M plus delta M. Why so? If you remember my last videos, I have already discussed that the value of shear force, or the value of bending moment can depend upon the distance from the origin, right? So here this is the origin, and the value will gradually increase along the beam as we increase the value of x, the value of shear force and the value of bending moment both will increase, right? So obviously the value of bending moment here and here will not be the same. Here the value of bending moment will be somewhat more than that of here, and obviously value of shear force will be somewhat more than that of in this, right? So we are taking the value of moment as m plus delta m and the value of shear force as v plus delta v in this plane. Okay, so now let's focus on the relation between the bending moment and the shear force. Okay, so for that we will be considering the summation of moment about a point is 0. So what point we are considering? We are considering this point P, which is on the beam. Okay. So as per the sign convention, I'll be taking anti-clockwise moments as positive and clockwise moments as negative. So the very first one, that is this will try to rotate this beam in a clockwise sense. So this will be negative m, right? And this m plus delta m will try to rotate this element in a anti-clockwise sense, so it will be positive m plus delta m. And obviously see, we have force like this shear force V, which will again try to rotate this beam in a clockwise sense, so it will be minus V. Now for calculating the moment, we will be multiplying this V with the perpendicular distance, that is nothing but x, right? This is x distance. This shear force is at a x distance from this B. Okay, so V delta x. What else we have? We have this, right? So W delta x will try to rotate the beam in anti-clockwise, so it will be positive. So positive W delta x is the force. So what will be the moment? This will be multiplied with this distance, that is this, right? So what is this distance? This is nothing but, this is the half of this thing, right? So it will be delta x upon 2. So W delta x multiplied with delta x upon 2. So this whole thing will essentially be equals to 0. Now see guys, delta x is a very small value, right? So the product of this delta x and delta x will be very infinitesimally small value. So what we can do is we can neglect this. So we can take this whole term as 0, right? And this minus m and plus m will get cancelled. So we will left with this. Okay. So if we subject the shear force, then we will be getting delta m upon del x. Delta x is shear force, and we already know, being a very small element, delta x will be tending to 0. So we will be left with this. So these are the two very essential equations or the relations that we were interested in, right? So basically, if I ask you what is the use or what is the significance of this equation, what can we conclude from these two equations? So the very first thing is, if you consider this equation, if you consider this particular equation, you can see the value of slope if you consider a moment diagram, a bending moment diagram, or a bending moment curve rather. So at any particular point, if you try to calculate the slope, suppose you have a bending moment like this, right? So at this point, if you try to calculate the slope, suppose this, so this will essentially denote the value of the shear force at that very point. Okay, this is the significance of this. And similarly, what can we conclude from this particular equation is that, suppose we have a shear curve that is somewhat like this. Okay, if you have a shear curve, so if you try to find the slope at a particular point in that particular shear curve, you will get the value of loading, or you will get the value of load at that particular point. So I will explain this with an example. So let us look at the example. So I have written these two equations here that we were interested in. So let us take this example. So this is a beam where two of the supports are given in these two ends. We have a UDL in this section BC, and the value of UDL is 8 kilonewtons per meter, and in this point D we have a point load that is 36 kilonewtons. Okay, so if we try to analyze this beam and try to build or try to draw the SFD and BMD, you will get something like this. Okay, now let us do one thing. Let us just focus on this BC section. Just forget everything else. Okay, just focus on this BC section, just this BC section. So if you take a look at the bending moment diagram at this BC section, this is essentially a parabola. Okay, and we already know that the value of bending moment will depend upon x. So I have written like this: there is moment as a function of x basically. Okay, so let us consider the equation. So first of all, this equation, this is a equation for quadratic. This is the graph for quadratic equation, right? So let us consider for this particular curve we have a equation like this. We have a quadratic equation like this. So what is this equation of moment, right? So what if we differentiate this? So if we differentiate this with respect to x, we will get, see, if we differentiate the moment with respect to x, we will get the shear force. So same thing, if we differentiate this with respect to x, we will get this, and this will essentially be your shear force. This is basically V, and I have written x within the bracket just because to show that the shear force is a function of x, nothing else. Okay, so the shear force is obviously a function of x. Now what will happen if we differentiate this again? See, if we differentiate the shear force, then we will get the load, right? Same thing, see, differentiating this equation, that is dv upon dx, we are getting the value -8. Okay, so guys, let's not focus on this negative sign, just focus on the magnitude, that is 8. The magnitude of this, that is dv upon dx, is 8. So if you again go into this diagram, you can see that the loading we have got is nothing but 8. The magnitude, after differentiating these two times, that is after differentiating the moment equation, then after differentiating the shear force equation, we have finally achieved the value of the loading, that is the value of the UTL. So now I hope this is very clear, the significance of these two equations. So these are quite very important equations. You should always remember this, or you should be very much conceptually clear the use of this equation. So I hope this video is very much clear. So if you like this video, make sure you subscribe to my channel, and if you have any doubt, please do comment in the comment section. Okay, so in the next videos I'll be uploading more problems in solving the shear force and the bending moment diagrams. But before that, this particular video was quite needed, was quite important, I could say. Okay, so please do wait for my next videos on shear force and bending moment diagrams. So till then, see you.